Hi everyone, I'm Tyler Hayes, and today I'm pleased to present our BMVC paper, Can I See an Example? Active Learning the Long Tail of Attributes and Relations. This is joint work with colleagues from the Rochester Institute of Technology, the University of Rochester, and Facebook AI Research. A preprint of our paper is available on arXiv, and our code is available on GitHub. In this paper, we incrementally train an agent to ask questions about a scene to better understand the scene's semantics. This could include asking questions about particular objects, attributes, or relationships within the scene that the agent is uncertain about. A human annotator could then provide answers or labels to the questions, and the agent could update accordingly. In short, our goal is to train an agent to better understand a scene while minimizing the number of questions it must ask a human annotator to answer. We study this problem using a task called visual triple completion. In visual triple completion, we provide the agent with a triple containing 2 known elements and 1 missing element. The agent must then complete the missing element in the triple using information from the scene. Elements in the visual triples consist of subjects, objects, attributes, or predicates, and we refer to incomplete visual triples as questions. Given these unique triple elements, we have 6 total question types that refer to either subject, predicate, object triples or subject, predicate, attribute triples. For example, here we have an example of a subject, predicate, object triple where the agent is provided with the giraffe subject, the hay object, and it must predict the missing predicate eating. Similarly, here we have an example of a subject predicate attribute triple where the agent is provided with the has attribute predicate, the orange attribute, and it must predict the missing giraffe subject. Given the 3 possible subject predicate object triples and the 3 possible subject predicate attribute triples, we have 6 total question types. While visual triple completion may seem straightforward, there are many practical challenges to solving this problem. First, the distribution of attributes and predicates in the natural world is imbalanced or long-tailed, with some classes occurring frequently and other classes occurring very infrequently. When trained in long-tailed settings, neural networks often overfit to the frequently occurring head classes and perform poorly on the less frequent tail classes. This problem could be worsened in an active learning setting if a neural network only asks about head class data and ignores tail class data. While the natural data distribution may be long-tailed, we expect our network to be performant on all classes regardless of their frequency of occurrence. Moreover, conventional active learning methods operate in the following way. Given an unlabeled dataset, they select a subset of examples to be labeled by a human annotator or oracle. The oracle then labels the subset of selected examples, and the agent updates on those examples accordingly. This process then repeats in several rounds. While straightforward, this conventional framework comes with caveats. First, it is time-consuming for an agent to perform inference over an unlabeled pool of examples to select a subset for labeling. Moreover, it is also time-consuming for an annotator to provide labels for the selected subset of examples. Additionally, this framing only allows the agent to ask questions that require a simple label as an answer, which could be limiting in practice. To overcome these caveats, we propose the Query by Category or QB-CAT active learning framework. We are motivated by the scenario where an agent may have knowledge of the classes that it needs to know about. It could then ask an oracle directly for examples from classes that it is uncertain about. For example, given the example at the bottom of this page, a conventional active learning method could ask for the label of the subject. In contrast, a QB-CAT active learning method could identify that it is uncertain about the predicate class eating and ask to see an example containing the predicate eating. An annotator could then provide this example to the agent. More specifically, a conventional active learning method would be provided with an unlabeled dataset. The agent would then compute uncertainty scores over the unlabeled dataset to select examples it is the most uncertain about to be labeled by an annotator. In contrast, a Query by Category active learning method would be provided with a dictionary of classes it is expected to know about. The agent would then compute uncertainty scores over classes and select the classes it is most uncertain about. An annotator would then provide examples from those uncertain classes to the agent. Using this framework, we introduce the QB-CAT tail active sampling method that prioritizes selecting data from tail classes of the dataset uniformly at random. we compare QB cat-tail to several conventional active learning baselines. Specifically, we perform experiments in an incremental active learning setup where each increment consists of the following steps. First, the learner queries an oracle for labeled data. Second, the learner updates on both newly labeled examples as well as previously labeled examples. Third, the learner adds the newly labeled examples to a memory replay buffer. And finally, the performance of the learner is evaluated. We perform experiments on the visual genome dataset and compute performance on the full test set, as well as a test set consisting of examples from only tail classes in the dataset. Here we are showing the main results of our QB cat-tail method as compared to several conventional active learning baselines. We show performance on the full and tail test sets in terms of AU-ROC and mean average precision. Each performance value is averaged across question types. Overall, we can see that our QB cat-tail method outperforms all baselines across test sets and metrics with strong performance on the tail test sets as expected. In contrast, we see that the performance differences among conventional active learning methods are minimal. In our supplemental materials, we find that these minimal performance differences are due to the conventional active learning methods selecting examples mostly from the head of the data distribution. Here we will look at the results across increments in a bit more depth. First, we will look at the results on the full test set for 3 different question types. Plots for the remaining question types are provided in our full paper. Overall, we can see that the performance of our method rivals the performance of conventional active learning methods, except on the box-based subject-predicate-object question where our method has strong performance. In contrast, on the tail test set, we see that our QB cat-tail method has strong performance across all 3 question types, outperforming baselines by a large margin. In summary, we introduced the query by category active learning framework and demonstrated how it can be used to train agents to predict objects, predicates, and attributes in visual scenes. We then introduced a simple yet effective active sampling approach using this framework that asks for examples from tail classes of the data distribution. We demonstrated the effectiveness of our approach on the visual genome dataset as compared to several conventional active learning baselines. Overall, our framework encourages future researchers to think about how agents should pose questions to an oracle to best improve their performance. Future work could look into extending our framework to the multi-element visual triple completion setting, exploring diversity-based active learning methods, or developing more query by category active sampling methods that make use of our findings. Thank you for your attention. If you have any questions, feel free to email me at the address listed at the bottom of this page or to stop by our virtual poster session during the main conference. Lastly, I'd like to thank my co-authors for their help throughout the project and the sponsors who helped fund me during the project. Thank you very much.